new chapter called equilibrium. Am I audible? फिर से एक बार पूछ रहा हूँ क्योंकि थोड़ा सा प्रॉब्लम है कवरेज में, इसलिए पूछ रहा हूँ। मैं आपको अब तक ज्वाइन भी नहीं कर पा रहा था कवरेज की वजह से। क्या मैं ऑडिबल हूँ? क्या आप मुझे सुन पा रहे हैं?
Yes,
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 sir.
sir.
That's great. चलिए then let us start the new chapter. The name of the new chapter is equilibrium. Let us study about the equilibrium in detail. In the last chapter, I have explained you some of the part of the equilibrium while solving some of the problem or while establishing the relationship between the equilibrium constant K and the Gibbs free energy. But that was just an introduction. Let us move ahead with more information about equilibrium. So chemical equilibrium, let us look into this matter. Chemical equilibrium, just 1 minute my dear students, there is something wrong, I think so. Okay, now it's working. So let's have a look to the discussion. Equilibrium. Chemical equilibrium are important in numerous biological and environmental processes. For example, if you look at equilibria involving O2 molecule and protein hemoglobin play a crucial role in transport and delivery of oxygen from our lungs to the muscle. Similar equilibrium involving carbon monoxide. This is carbon monoxide, please pay attention. This is carbon monoxide. So similar equilibrium involves carbon monoxide molecules and hemoglobin account for the toxicity of carbon monoxide. So this is how the equilibrium established between the carbon monoxide and hemoglobin causes the toxicity in our body. When a liquid is placed in a closed container, some molecules of the liquids leaves the surface of liquid state from the surface and go to the vapor state. Same way, my dear students, from the vapor phase, some of the molecules strike the liquid surface and are retained in the liquid phase. So this is what it happens, that some molecule go to the liquid phase, some they come back, and again from liquid state they go to the vapor phase and they come back again to the liquid state. When from liquid state molecule goes to the vapor state, vapor pressure increases. So when molecules from the liquid state go to the vapor state, it's obvious to understand that as the number of molecule increases in the vapor phase, they create more vapor pressure and thus the vapor pressure increases. From vapor phase, molecules come to liquid state and vapor pressure decreases. So vice versa, if the molecules comes to the liquid state, the vapor pressure decreases. But when we measure the vapor pressure, we find it remains constant and does not change frequently. So whenever we measure the vapor pressure, after some time we find that yes, the vapor pressure remains constant. So why the vapor pressure turns constant after some time, or why do we find when we measure the vapor pressure is constant? The vapor pressure is constant because this is because of equilibrium. When the number of molecules going from liquid to vapor and number of molecules going from vapor to liquid are equal, both the number of molecules going from vapor to liquid and liquid to vapor become equal. That means the rate of evaporation and the rate of condensation become equal. So the rate of evaporation and condensation become equal. We say equilibrium state is obtained. In this condition, when the rate of evaporation and rate of condensation become equal, we say that there is an equilibrium established, and it is represented by the double-sided arrow. So this is how we represent the state of equilibrium, my dear students. So this is the symbol for the equilibrium. You can see here between the H2O liquid and H2O vapor, we have represented the equilibrium that has been established by the double-sided half arrow. The double arrow indicates that both the processes are undergoing simultaneously and none of the reaction has come to an end. So both the processes are going simultaneously and none of the reaction has come to an end. कोई भी रिएक्शन पूरी नहीं हुई है, दोनों रिएक्शन चालू है और ये रिएक्शन चालू होने के बावजूद भी अपना जो इक्विलिब्रियम प्रेशर है, जो वेपर प्रेशर है, वो कांस्टेंट बन चुका है, क्योंकि दोनों प्रोसेसेस का इवेपोरेशन का और कंडेंसेशन का रेट जो है वो बिल्कुल सेम हो चुका है. दैट इज द मेजर रीजन. नाउ लेट अस अंडरस्टैंड व्हाट इज इक्विलिब्रियम मिक्सचर. द मिक्सचर्स ऑफ रिएक्टेंट्स एंड प्रोडक्ट्स in the equilibrium state is called an equilibrium mixture. So this is how, my dear students, we understand about the equilibrium mixture. Now let's move forward and understand. Equilibrium is dynamic, and at equilibrium neither forward reaction nor backward reaction has come to an end. Just the rate of forward reaction and the rate of reverse reaction become equal. Please remember that there is no end of any kind of reaction, either forward or backward, but simply the rate of both the reactions become equal, and as the rate of both the reactions become equal, we consider that it is an equilibrium. None of the reaction has been stopped. In equilibrium mixture, there is no change in the concentration of reactants and products. So in the equilibrium mixture, there is no change in the reactions at equilibrium, either for the reactants or products. At equilibrium stage, there is no change in concentration. So at equilibrium, we don't find any change. Depending upon the concentration of reactants and products, equilibrium can be three types. So we can have three types of equilibrium depending upon the concentration of reactants and products. Number one type, let us move. The reaction that proceeds nearly to completion. That means more amount of product is formed and less amount of reactants are available. And only negligible concentration of reactants are left. And in some cases, the concentration of reactants is not possible to detect experimentally. So the reaction goes in a forward direction to such an extent that the existence of reactants is not even possible to measure, not even possible to detect at the end of the, or when the equilibrium has been established. That is the kind of equilibrium when this was the first type of equilibrium. Now we'll study about the second type of equilibrium, the reaction in which a small amount of product is formed and most of the reactants remain unchanged at equilibrium stage. So the reaction in which a small amount of product is formed and most of the reactants remains unchanged at equilibrium. That is the equilibrium where the reactants does not react much to give us the product, and in that particular case, the concentration of reactant is more than the concentration of products. And then we have the third type of equilibrium, where the reaction in which the concentration of reactants and products are comparable when system is in equilibrium. So both the reactants and products have almost equal type of concentration, or both the reactants and products are available at equilibrium in a good amount, or in the amount where the equilibrium, or where the concentration of products and concentration of reactants are comparable. Now, my dear students, we want to study the new definition, which is known as the ionic equilibrium. So equilibrium involving ions in the aqueous solution, which is called the ionic equilibrium. So at equilibrium, my dear students, if ions are available, such equilibrium, ions are present in both reactants and products. Such equilibrium is known as the ionic equilibrium. Now let's move forward. equilibrium in physical processes. So first we will study how in the physical changes, there are various physical changes and how in various physical changes the equilibrium is established. The best example of equilibrium in physical processes are phase transformations. Phase transformation means conversion of solid into liquid, or equilibrium that is established between the solids and liquid, equilibrium that is established between the liquid and gases, equilibrium that is established between the solids and gas. So solid and liquid equilibrium. Let us first understand about the solid liquid equilibrium. If in a perfectly insulated thermos flask, we have already studied that thermos flask which is perfectly insulated behaves like an isolated system, and during this, or when we put something into the insulated thermos flask which is perfectly insulated, there is no exchange of heat as well as there is no exchange of mass. So neither the temperature changes or not the number of mole changes. Where no exchange of heat and the heat remains constant. So in a insulated, perfectly insulated thermos flask, and there is no heat change between the system and the surrounding at 273 Kelvin. Now, why do we maintain this temperature 273 Kelvin? Because we want to understand the change into the solid, that is ice, and the liquid, that is water. So it is the melting point of water, that is 273 Kelvin or 0 degrees centigrade. And at 1 atmospheric pressure, which is possible, we put ice and water in it and find that when we put ice and water into the perfectly insulated thermos flask, we find that mass of ice and water does not change at all because it is insulated thermos flask. Temperature remains constant into an isolated system. So there is an equilibrium established between the ice and water. So we can say ice and water has an equilibrium established, or you can say that H2O solid and H2O liquid has established an equilibrium between these two phases. However, the equilibrium is not static. Not static means not stopped. Not stopped. Or my dear students, we can say that both the forward and backward reactions are going on. It is not stopped, or at equilibrium, none of the forward reaction or backward reaction has been stopped. The intense activity can be noticed at the boundary between the ice and water. So where there is a boundary between the ice and water, there is an intense activity going on. Ice is converting to water and water is converting to ice, but still the concentration of water and ice has not been changed. At the same time, the temperature also has not been changed during at equilibrium, when equilibrium has been established. We can say it is a dynamic equilibrium. So such equilibrium or such condition when both the reactions are going on, they have not been stopped, but the concentration and other parameters remains constant. Such a state of equilibrium is known as the dynamic equilibrium, because the equilibrium, the processes are going on, but still it is a stable condition. That is what we have seen even into the definition of the equilibrium. Uh, Conversion of ice into water and water into ice is going on, but the mass of the water and ice does not change. The temperature does not change, and that is why we call it as a dynamic equilibrium. Here, rate of forward reaction and rate of reverse reaction become equal. That means the rate of forward reaction and rate of reverse reactions are even constant. So not only mass and temperature, but the rate of reactions for forward and backward even become constant. Ice and water can be in the equilibrium state at particular temperature only. So my dear students, at equilibrium, if we change the temperature, then we can understand that the uh, the mass and the temperature will be changed, and the equilibrium or a new kind of equilibrium will be established for a particular temperature. The equilibrium state is constant, but if we change temperature, the equilibrium state is also being changed, and at a new temperature, a new equilibrium can be established. For any pure substance at atmospheric pressure, the temperature at which the solid and liquid phase are at equilibrium is called the normal melting point. Please remember, this is the definition of the normal melting point in the reference of equilibrium. In the reference of equilibrium, my dear students, we can define the normal melting point, and what is the new definition that we can write for the normal melting point? That for any pure substance at atmospheric pressure means at 1 atmospheric pressure, that is what they mean to, which is 1.013 bar. So that is the 1 atmospheric pressure, and at 1 atmospheric pressure, the temperature at which the solid and liquid phase are at equilibrium is called normal melting point, or it is also called normal freezing point of the substance. At equilibrium, which is dynamic, we can infer, or from all this discussion, now we can say about equilibrium that both the opposing processes are simultaneously occurring. So none of the process has been changed. Both the process occurs at the same rate. The rate of forward reaction and rate of reverse reactions are equal. Thus, the mass of ice and the mass of water remains same. So at equilibrium, the rate become constant, the mass become constant, and the temperature has also become constant. Now, my dear students, we want to study about the liquid vapor equilibrium. Before we start, my dear students, if you have any question, you can ask me. बच्चों, अगर आपको कुछ समझ में नहीं आया है तो आप मुझे पूछ सकते हैं और बता दीजिए कि समझ में आ गया है, तो वी कैन मूव फॉरवर्ड प्लीज.
हाँ सर, समझ में आ रहा है.
ठीक है, थैंक यू बच्चों, थैंक्स फॉर योर नाइस रिप्लाई. लेट्स मूव फॉरवर्ड. Let us understand the liquid vapor equilibrium. In a transparent box, remember we are going to take a transparent box. In a transparent box carrying a U-tube with a mercury. Remember, this U-tube with a mercury is known as manometer, and this manometer is used to measure the pressure. So we take a transparent box, and in transparent box we fix manometer so that the pressure inside the box we can measure. Let us put a drying agent such as CaCl2 calcium chloride or phosphorus pentoxide P2O5. My dear students, this CaCl2 or P2O5 are the drying agent, and they actually absorb the moistures. So what is the meaning of drying agent, my dear students? Drying agents are the substances that absorbs the moisture. I hope you understand, moisture is your water vapor H2O gas. So if some of the moisture present into the transparent box, this CaCl2 and phosphorus pentoxide will absorb this moisture from the box itself, and to absorb the moisture we put this drying agent into it for a few hours. So if we put them for a few hours, what happens? All the moistures inside the mixture has been absorbed. Then what happens? Then let's put a watch glass or petri dish containing water by tilting. Tilting means just making it to move in a particular angle, not by suppose this is the box. So if we tilt it in this way, this is what it is known as the tilting. So the box was initially in this manner, but then we changed the angle with the surface at bottom, and thus we can tilt it. So by tilting the box, we just by tilting the box, my dear students, the box we quickly put this water containing the watch glass containing water or the petri dish containing water, we put immediately inside this box by tilting it very easily. Now what happens? Let us move. You can see here the figure. Tube containing mercury is called the manometer. You can see here we have a transparent box. In this transparent box, my dear students, we have first we have joined this manometer. This is what it is, the manometer. And here we have anhydrous calcium chloride, CaCl2. So all the moistures present inside the box can be removed. And then, my dear students, we after some time we put water. This is the watch glass or petri dish in which we put the water by tilting it and quickly, and then we can measure the pressure inside the transparent box. Uh, Let us see what is being observed. It is observed that the mercury level in the manometer increases. You can see, my dear students, initially there was a mercury level which was almost equal, but later on what happens, the mercury level increases. So initially it was in this condition, but finally what happens, the mercury level increases to certain extent. Suppose this is the increase into the mercury level. So mercury level rises into the manometer when we put water inside the transparent box. Mercury level increases initially due to the formation of vapor from the water, but after some time, the level of mercury becomes constant and it does not rise any further. So, my dear students, after this much of increase into the level of mercury, now the level of mercury does not rise any further. Volume of water in watch glass decreases. So as the volume of water turns into the vapor, the volume inside the watch glass even decreases. And after some time, the volume is even constant and no further decrease in the volume. So initially some of the volume of the water decreases, and after some time in a closed container or in a closed system, the volume of water even remains the constant and that does not change. Here in this condition, rate of evaporation is equal to rate of condensation. Here in this particular condition, my dear students, we can say that the rate of evaporation is equal to rate of condensation. Therefore, liquid vapor equilibrium is established. So here in the box, now we can say that there is an equilibrium established between the H2O liquid and H2O vapor. That means that means here also inside the box now no temperature change, no change in the concentration, no change in the rate of the forward reaction as well as the backward reaction. It means there is no change, or the rate of evaporation and rate of condensation become same. So, my dear students, here we find some pressure that we measure. That pressure we want to define here as an equilibrium vapor pressure. Let us learn the definition of the equilibrium vapor pressure. At equilibrium, the pressure exerted by the water molecules at a given temperature, remember the temperature needs to be constant, remains constant and is called the equilibrium vapor pressure of water. So at particular temperature, for water if it is placed into a closed system, the vapor pressure turns out to be constant. At equilibrium, the vapor pressure exerted by water vapor is known as the equilibrium vapor pressure. Now, if we increase the temperature, my dear students, inside the box, the vapor pressure increases. So when we increase the temperature inside the box, the vapor pressure increases, and that is why we can say that the vapor pressure is directly proportional to the temperature. Now we are going to perform some other experiment in the same kind of box. Now if the above experiment is repeated with methyl alcohol, your methyl alcohol is nothing but CH3OH, acetone, that is your CH3CO, CH3, and ether, that is, let us say it is diethyl ether, CH3O, CH3. So now we put the another kind of liquids into this box and understand this experiment. It is observed that when we put these liquids into the box, we observe after some time, we observe that these liquids have different equilibrium vapor pressure at the same temperature. So all these three liquids, either it is methyl alcohol, acetone, or it is ether, all these three liquids also gain the equilibrium state, and their equilibrium state is different from the equilibrium state of water. How does it differ? That at equilibrium, the vapor pressure exerted by methanol is different from the equilibrium vapor pressure of water. The equilibrium vapor pressure of acetone is different from the equilibrium pressure of water. The equilibrium pressure of ether is different from the equilibrium pressure of water at same temperature. At the same time, for all these three liquids also, their equilibrium pressure is different from one another at the same temperature. That means different liquid exert a different equilibrium pressure at a certain temperature. That is what we can easily say. So the liquids which has a higher vapor pressure is more volatile and has hence lower boiling point. So please remember, my dear students, that out of these four liquid, one you have the water first, then you have methyl alcohol, then you have acetone, then you have ether. Out of these four, the liquid which has got the more volatile nature will have the highest equilibrium pressure, and as the liquid has the highest equilibrium pressure, we can say that it will have the lower boiling point. So we can even easily understand that if from the equilibrium pressure, that those liquids which have higher boiling point, or sorry, those liquids which have lower boiling point will have the highest equilibrium vapor pressure. If we expose three watch glasses, now we want to expose the three different watch glasses containing separately 1 ml of each of acetone, ethyl alcohol and water to the atmosphere and repeat the experiment for the different volumes of liquid. Now, my dear students, we want to expose the three alcohol and we want to measure. Once again, let me tell you. Now what we do, we expose three watch glasses containing separately 1 ml of each. So in each watch glass, we have 1 ml of acetone, 1 ml of ethyl alcohol, 1 ml of water to the atmosphere and repeat. So first we will put only 1 ml. In the next experiment, in three watch glass, we will put 2 ml. In the third experiment, we will put 3 ml. Thus we change the volume of these three liquids and observe what happens. Let us look at the observations that we may get. We observe that the liquid in all three different types of we observe that the liquid in all three types of liquid disappears. When the liquid disappears, when we put them in when we put them into the box which is open. So please remember that this new experiment we have been doing at the open system, not into the closed system. If we expose three watch glasses containing expose means, my dear students, we have put them into an open system, This means when we take the three watch glasses, we put them into the room. We do not put them into the transparent box where we have placed the transparent box containing the U-tube or manometer. Now we are going to put, or in the next experiment, we are going to put them into an open room or into an open system. When they are put into the open system, my dear students, and when we change their volumes, what we observe is this, that we observe that liquid in all three different types of liquid disappears. Disappears means they vanishes. They do not remain, or they do not put themselves left into the watch glass, and they completely undergo the process of evaporation. None of the liquid has been left into the watch glass or petri dish any further. And time taken for complete evaporation depends upon the time taken to complete evaporation depends upon the nature of the liquid, the amount of the liquid, and the temperature. So, my dear students, when these liquids disappears, depending upon what kind of liquid you have taken, the time required to complete evaporation depends. How much liquid? Suppose you take 1 ml, then it requires less time. But if you put 3 ml, then it requires more time. If you change the temperature, so at lower temperature, the rate of evaporation is lower, and at higher temperature, the rate of evaporation is higher. Even when we compare this alcohol, ether, uh, alcohol and ether, we find that ether can easily evaporize, whereas alcohol will not be easily evaporized. Same way, my dear students, if we compare it with the acetone and ether, the acetone will be evaporizing faster as compared to the alcohol. So this is how, when we have the different materials take the, so alcohol will take more time than the ether as well as the acetone for complete evaporation. That is why the time taken for complete evaporation depends upon the nature of the liquid, depends upon the amount of liquid, what is the volume that we have taken, depends upon the temperature. When watch glass is open to the atmosphere, the rate of evaporation remains constant, but the molecules are disappeared into the large volume of the room. Now, why does it happen? Why all the volume goes away? Because all the volume of acetone or methyl alcohol or ether that we have taken, it goes inside the room temperature, and ultimately all the liquid disappears. As a consequence, the rate of condensation from vapor to the liquid state is much less than the rate of evaporation. You know, outside, when there was a closed system, there was a room for there was a less room for vaporization of the molecules, and that is why after some time the equilibrium has been established. But here the room has a great volume, and the liquid that we have taken into the petri dish or the watch glass is in a very small volume. Ultimately, what happens? This small volume can be completely evaporized into the large volume, and the small volume cannot generate the pressure that is enough, or that can be have equilibrium between the liquid state and the vapor state. And due to the large volume of the room, the equilibrium cannot condense or the equilibrium cannot be established. So from this, my dear students, we understand that it is not possible to reach equilibrium in an open system. If we keep the system open, if we do not use the closed system, the equilibrium cannot be established. So my dear students, it is an important point that we come to conclude here, that equilibrium can only be established into the closed system. If heated up to 100 degrees centigrade, if heated up to 100 degrees centigrade temperature in a closed vessel or in a closed system, water and water vapor are in the equilibrium position at atmospheric pressure, that is 1.013 bar, and at 100 degrees centigrade, that is boiling point of water, at 1 atmospheric pressure, and at 100 degree centigrade or 373 Kelvin. So when we heat these liquids, or when we heat water into a room, my dear students, the equilibrium can be only established at 100 degrees centigrade temperature only. So when we increase the temperature, the rate of evaporation increases, and at 100 degrees centigrade, my dear students, there will be an equilibrium established between the two reactions. One is the evaporation and another is the condensation. And that is what it is, the point which is known as the boiling point of the water. For any pure liquid at atmospheric pressure, that means 1.013 bar pressure, and the temperature at which the liquid and vapors are at equilibrium is called its boiling point of it, or it is the boiling point of the liquid. So this is how, my dear students, we determine the definition of the boiling point. Let me tell you once again, what is the definition of boiling point in reference to the equilibrium. For any pure liquid, we are talking about any liquid, please note, at atmospheric pressure, that means 1.013 bar, the temperature at which we are thinking about the temperature at which the liquid and vapors are at equilibrium is called the boiling point of it. That means when at a particular temperature, when there is an equilibrium established between the liquid phase and the vapor phase, such equilibrium or such state as at this equilibrium, the temperature what is at what, like whatever the temperature the equilibrium is established, that particular temperature is called the boiling point of that liquid. Boiling point of a liquid depends upon the atmospheric pressure and the altitude of the place where the boiling point is measured. Please remember, my dear students, that boiling point of a liquid depends upon the atmospheric pressure. If atmospheric pressure is 1.013 bar, we can say the boiling point is 100 degrees centigrade for water. But if what happens, if the atmospheric pressure decreases, then the water starts boiling at lower temperature. If the atmospheric pressure increases more than this, then the water has to be boiled at higher temperature. We have even studied into the previous chapter that we use cooker to increase the boiling point of water. Same way, my dear students, altitude of a place where boiling point is measured. If the boiling point is measured at higher altitude, means higher altitude than the sea level, the boiling point decreases. At high altitude, the boiling point decreases, and that is why the places where we have higher altitudes, it is suggested to use cooker for cooking. Now, my dear students, in the next step, we want to study about the solid vapor equilibrium. My dear students, if you have any doubt, you can ask me. Do you have anything to ask? बच्चों कुछ पूछना चाहेंगे? If you want to ask, you can ask or tell me you understood. Please reply, my dear students.
Yes, sir.
Okay, let's move forward and study the solid vapor equilibrium. If we put solid iodine in a closed vessel, after some time, the vessel gets filled up with the violet vapors and the intensity of color increases with time. Please remember that when we put a solid iodine in a closed vessel, after some time, the vessel gets filled up with the violet vapors and the intensity of color increases. So slowly, the color inside the vessel become more and more violet, or from light violet, it goes to the dark violet color. After containing the, after certain time, the intensity of color become constant. So after some time, for some time the intensity increases, and after some time the darkness of the violet color inside the vessel become constant. Now there is no further increase into the darkness of the violet color, and at this stage equilibrium is attained. So we say that at this stage the equilibrium has been attained. Hence solid iodine sublimes to give iodine vapor, and iodine vapor condensed back to give the solid iodine. The equilibrium can be represented as I2 solid, which gives I2 vapor. So the equilibrium that has been established in this case is known as the solid vapor equilibrium. So my dear students, we can understand the solid vapor equilibrium with the example of our iodine solid and iodine vapor. Apart from this, we can even understand in the case of the camphor or naphthalene or in ammonium chloride. So those substances which can sublimate, using them we can understand the solid vapor equilibrium. I hope, my dear students, up till now you have understood everything. बच्चों, क्या आपको सब कुछ समझ में आ गया है? अगर आप कुछ पूछना चाहें तो पूछ सकते हैं. क्या आप मुझे सुन पा रहे हैं?
Yes, sir.
Yes,
Okay,
sir, सुनाई दे रहा है.
let us do the required revision now. Let us not go further.